Hello, it's John, here with another not quick enough video. What we want to look at today is thinking about derivatives of inverse functions. We've figured out the derivatives of the basic functions, derivative of sine and cosine, derivative of power functions, derivative of exponential functions. We can find these things using patterns and understanding um, what we're seeing in those patterns to be able to generalize. Some functions, if we think about them, we don't really know kind of where to get started with the derivatives. What if we had the arc cosine? Right? We know that is a very mysterious function. All we know about it is that it's an inverse. So if we had another function that was cosine, that if we compose those things, they undo each other. In other words, x goes into g, g of x goes into f, and then out comes x again. And in fact, if mathematicians are honest about it, one of our major obsessions, once we know how to do something, is how do you undo it, right? So figuring out one direction for cosine, how would we go? Cosine takes an angle and gives us a number between 1 and -1. How could we go from a number from between 1 and -1 and figure out which angle it is, right? If we can do something, we want to be able to undo it. In this comic, it also brings up redoing. That's a slightly smaller fixation, but mathematicians also want to know what happens if you do something again and again and again. And we've seen that a little bit with one derivative wasn't enough. We had to do a second derivative. Okay, so since inverse functions are about composition, that means we're going to be talking chain rule. Right, so if we make a new function, we've got some function f and we've got some function g. We know the chain rule tells us how to take the derivative of this whole thing. And you see this expressed lots of ways. It's the derivative of the outside function, keeping the same inside, times the derivative of the inside function, which maybe you see the idea that you're putting the x into that, right? Thinking about it as a function. Okay, so we're going to use this. This means that we could figure out something about this function if we know the derivative of the inside. Right? So this is an application of the chain rule. And why it's particularly good for inverse functions is that what makes functions inverses is that if you start at x, g goes to g of x, f takes it back to where we came from, which is the x. So, but if we take the derivative of one side, it's still equal if we take the derivative of the other side. Now, we haven't really proved that yet, right? So we're relying a bit on intuition. We have an equation, and if we think about what we do to one side, it's going to be equal if we do the same thing to the other side, right? So, but in this case, that intuition turns out to be correct. We can take the derivative of both sides and maintain equality. And if we take the derivative of x, that's just 1. How does x change with respect to x? Dx by dx, that's 1. Just like the notation would suggest it would be. We have the chain rule that tells us what this looks like. And we know what this other side looks like, and that allows us to come up with an equation for something. Okay, so we're going to start with the example of natural log and e to the x. So in some of our exercises, we've made reference to what the derivative of the natural log is. So maybe you've looked it up, maybe you've skipped past those problems, but here's where we can start to think about kind of where is it coming from. We know the derivative of e to the x because we know the derivative of exponential functions, and this one is that lovely function where if we take the derivative of e to the x, we get e to the x. Okay, so if we didn't know the derivative of the natural log, this inverse function relation would let us figure it out. So it's going to come from the fact that these are inverses. So the natural log of e to the x is x. Right? So we can take the derivative of both sides. We use the chain rule for this. So we've got the derivative of this function, and it's not multiplied by e to the x. We're thinking about putting that inside the derivative. So this is kind of holding our place for f prime of g of x here in the chain rule. Now we're going to multiply that times the derivative of the inside function, the derivative of e to the x, which is just e to the x. Okay, and that's equal to the 1 from when we took the derivative of x. So in other words, we can play with this equation, right? We've got this function, we don't know what it is, but we know its derivative when we put in e to the x is 1 over e to the x. So in other words, the derivative of the natural log of something is 1 over the something. Right? So this is why we say the derivative of the natural log of x is 1 over x, because x is the mathematician's favorite notation for something. Okay. This is super weird, right? So this is a place where we have to have insight. We have to be able to relate kind of what's happening in our function here with what's happening over here. So sometimes we'll be able to do that, sometimes we won't be able to do that. This is one of the first things we've seen with derivatives that somehow doesn't always work. Okay, so we're going to do 2 more examples. We're going to think about this one reversed, and then we're going to finish up with that example of cosine and arc cosine, right, when things get really weird. Okay, so this time we want to switch and we want to think about, we said that f of x is natural log of x, and g of x is e to the x. So if we do g of f of x, but the main point is, right, thinking like a mathematician, these are inverse functions, so when we compose them, they just go back to where we started. We put in an x, we get out an x, because we did the f, then the g, or like on the previous slide where we did the g, then the f. So if we want to take the derivative of this, so f of x was this ln of x, the natural log of x. So we're saying that when we put the natural log in here, when we evaluate that in the derivative of e to the x, the derivative of natural log if we're to believe what was on the previous slide, is 1 over x. Right? So the derivative of e to the x, that was our g, when you put in ln of x, we get out x, right? But we're saying it's the function that when you put in ln of x, you get x out. That means it has to be the inverse function of ln of x. But what is the inverse function of ln of x? It is e to the x. So we could stop and say we know there. If we don't, right, this is the spot where we have to think, how do x and natural log of x relate? And e to the natural log of x is equal to x, right? Which means that we're saying this inverse function of ln of x is equal to e to the ln of x. In other words, our inverse function of blah is e to the blah. But the function of blah, e to the blah, what that's saying is that dg of x is e to the x. So we could start out with the derivative of natural log, or start out with the derivative of e to the x, the exponential function, and find the derivative of the other one by using this inverse function relation and the chain rule. Okay, well, those ones we knew. How will this work out for cosine? So this is the one, the derivative we know. Maybe you remember the derivative of sine is cosine, and the derivative of cosine is negative sine. How do you remember that? How do you keep straight which one is positive, which one is negative? G prime, the derivative of arc cosine, we do not know, right? So we are going to put it together with the one we don't know as the outside function, because what we know about is that f prime. So we're going to see if that helps, right? And what we know about inverse functions, when you compose them, you get out the same thing you put in. And so when we do the derivative of the left side, you get the derivative of the outside function times the derivative of the inside function equals the derivative of x, which is 1. So this derivative we're looking for, when we put cosine in it, we'll be able to say something here. So when we put cosine in the derivative of the arc cosine, the inverse cosine, we get minus 1 over sine x. So remember, this is where the arc comes in. So we have to think about how do sine and cosine relate. Well, the main way we think about connecting these two things is from what's called the Pythagorean identity, which connects back to the unit circle idea about trigonometric functions. One way to think about sine is as the square root of 1 minus cosine squared x. So the square root of 1 minus cosine squared x. Right? So what that's going to mean is minus 1 over the square root of 1 minus cosine squared x. Now we took a square root, So we should remember at some point to think about, well, what if we had picked the negative 1 minus cosine squared of x? Right? Because square roots, the square root of 4 is 2 or negative 2. Right? So we've made a choice here, and we're going to see kind of how it works out. So the derivative, when we put in blah, we get out minus 1 over the square root of 1 minus blah squared. Holy cow. So what this means, what we're saying is that if we put x in for the blah, we're going to get minus 1 over the square root of 1 minus x squared. So we're saying that the derivative of the inverse cosine is something completely non-trigonometric. Negative 1 over the square root of 1 minus x squared. So we have to try to verify this, okay? Because that's quite a claim. So previously in Desmos, I put in these functions so we could look at them quickly. So the arc cosine, it looks like the cosine function flipped over the line y equals x. So some things to notice is that we put in the number between negative 1 and 1, and we get out an angle between 0 and pi, right? We could have negative values, right? So for a given cosine value, there's a positive angle and a negative angle that have the same cosine. But, so we had to make a choice to make arc cosine a function. If we had kind of drawn in the reverse of the whole sine or the whole cosine curve, it's not a function anymore. So to make it a function, we're picking a piece of it. It goes all the way from negative 1 to 1. And Desmos, very good, can graph. What does that look like? Well, it's interesting, right? So it's all negative. The slope as we get off close to negative 1 is infinite, right? It's going infinite. So this is a vertical asymptote here, and then that means the derivative is going to have this vertical asymptote as well. And then as we come up towards 1, right, as an input, we're getting 0 out, but again, it's infinitely steep. So we get this. So what does the graph of minus 1 over the square root of 1 minus x squared look like? We do notice it's undefined when x is negative 1 and positive 1. That's a good sign. It's the same thing. Okay? So this worked, right? This crazy idea of taking derivatives and then doing a little bit of hand waving, trying to think about how what we got on one side relates to what we were putting in, it works. Not always, not every function, but often we can get some insight into the derivative of what is a very strange function, obviously, right, that we get this. Okay, so the last thing to think about would be, well, what about that negative square root? Well, like I said, we could have defined our cosine to think about the negative angles. And then the derivative would look like this, always positive. And if we change the square root to taking the negative square root, it matches again. Right? So choosing the positive or negative square root turned out to be kind of equivalent to when we made the choice for arc cosine. Did we want a positive angle out or a negative angle out? And somewhere along the line, mathematicians said, for the most part, we're going to think about getting positive angles out of the inverse cosine. All right, so that is how we use the chain rule to find derivatives of inverse functions. It's the power of these ideas, right? The derivatives, the strong relationships we have, our understanding of functions and how functions can compose lead to us being able to find derivatives of some very mysterious functions. And that's it for this video. Thanks very much for watching.